Hello everyone, welcome back. This is Calculus 3. In this video, we are going to talk about 4.4, tangent planes and linear approximation. In this section, we're going to consider the problem of finding the tangent plane to our tangent plane in three-dimensional space, which is very similar to finding the equation of a tangent line when you were dealing with one variable in Calculus 1 and 2. So what is the slope of tangent plane, which is going to be very similar, the slope of the tangent line with the one variable. So let's take a look at that concept here, okay? So here we go. It's a little bit of a, background of tangent line. So if you guys remember, when we are dealing with one variable, so it's a very thick. So when you remember, we had a function, and let's say I have f of x function, and I want to find out the tangent line that is touching at this point. So there are infinite points on the line, but I want to find out the line when x equal to a. So the line that is a touch, like very, 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 touch this, only this line, we call this is a tangent line. And then to find out the tangent line, it was y equal to mx plus b. And then slope of the tangent line, you can find out by taking the derivative of the given function. So that was the concept we learned how to find out the tangent line in Calculus 1. We are going to find out tangent plane, which is a very similar tangent line. So let's take a look at that image. So in three-dimensional space, right? So you have the point. So let's say I have a, y-axis, x-axis, and z-axis. So let's say we have, here, this is x0, y0, z0. And then you can find out the line. So there is a many possible, lines that they're passing through this point, right? So there are infinite lines they are passing through this point. But I'm not looking for the line. I'm looking for the plane that covers the points. The plane touches a particular point. So as you see that image, it's a little bit hard to imagine. So here, as you see that there are infinite lines are passing through this moment, but I want to find out the plane that covers this moment where the infinite lines are passing through this moment. So we call that as a tangent plane. And then very similar, we're going to find out the slope. We're going to find out the whatever other y-intercept. The formula is going to be this. So to find out the equation of the tangent plane, so this is a kind of like a y-intercept. So you're going to find out f of x 0, y 0. So you're going to take the partial derivative with respect to x. And then x minus x 0, partial derivative of the y. And then when you collect this one, we call this is the equation of the tangent line, okay? So this is the background, which is very similar, to finding the equation of the tangent line. So you have a many tangent line at this moment. We are looking for a particular plane that covers that moment, right? So we call that as a tangent plane, and the equation is the following right there. And then sometimes, depending on the textbook, f of x0, y0, we can also write it as a z0. So we know how to find out that. But you need to find out the derivative, partial derivative with respect to x and y. So that's a kind of the same function of the slope of the tangent plane. Okay, so we are going to find out tangent plane, right? So as you see that, it's a very understandable topic. Nothing is, complicated. So let's take a look at the example. So you are going to remember this two formula, either one or second one, doesn't matter. They're talking about the same thing. This is the plane, tangent plane that touch only this, moment. So that's what the tangent means. So let's take a look at the example one right there. So I'm gonna write it. Tangent, the equation of the tangent plane is z equal to f x0, y0 plus the partial derivative x0, y0, x minus x0. I just need a little bit of space. Plus f of y, x comma y, x0, y0, y0, y minus y0. So this is the formula of the equation of the tangent line. So we have a given function of f of xy, two variable. So let's find out step by step. And then they're looking for the tangent plane at the moment 2, -1. So fx0, y0, this is something I want to find out at 2, -1. So what is it? You're literally going to plug in 2, -1 into this equation, correct? So that is going to be 2 times 2 squared, 3 times 2 times a -1, 8 times -1 to the second power, 2 times 2, -4 times -1, and 4. So if you calculate it, it should be 34. And now I'm going to find out, so we just finished this part. I'm going to find out the partial derivative with respect to f of xy, f of x, and then x0, y0. And we're going to find out that, so partial derivative, d over dx, we have 2x second, 3xy, 8y second, 2x minus 4y plus 4. And you are particularly, take the, derivative with respect to x. So f of x, so it is going to be 2x second will be 4x. And then 3xy, y, we are going to consider as a constant. So it'll be just 3y because x is going to be 1. And then this is just going to be what? Y is going to be the constant. So they are going to be, what do you guys think? 0. So these are going to be 0. And then we have a 2. And then 4 will be 0 as well. So constant will be 0. So this is the f of x, partial derivative with x with respect to x. And I'm looking for partial derivative of this at 2, 1. You're going to plug in. So 4 times 2, 3 times 1, plus 1. So 8 minus, actually this is -1. So it's going to be double negative change to positive. So we have a 13. So keep going. I'm going to make it a little bit smaller. Let's find out partial derivative with respect to y variable. So we are going to copy this, paste. So we are going to take the partial derivative with respect to y. So 2x second, what do you guys think? This is going to be constant, so we don't have anything, so that's going to be 0. And -3x, now x is a constant, so -3y, 16y, 2x is going to be constant 0, -4, and 4 will be 0. So f partial derivative with respect to y at 2, 1, -3 times -1. And then what happened? Actually, I have a typo. This one should be x, isn't it? This one should be, because y is we are taking the derivative with respect to y, so 3x remaining. So my bad. So -3 times 2 plus 16 times -1, -4, it should be -26. So all we got this information. Am I correct? We got those are 3 information. So therefore, the z, we are looking for the equation of the tangent plane. That would be 34. So let me just copy this one more time. Copy and paste here. So we have all the information, isn't it? So z equal to f of 8x0, this is a 34, plus 13, x minus, and then this is x0, y0, so -2, and then y partial, -26, y minus 1, because that's your y0. So if you simplify, is equal to 34 13x minus 26 minus 26y. This is a positive times negative, negative 26. So basically z equal to 13x minus 26y minus 18. This is going to be the tangent, the equation of tangent plane at 2, negative 1. So that's we can find out. Okay, so finding the equation of the tangent plane, it's not really complicated. As long as we're using that equation, we know how to take the partial derivative, and then the given point will be, here, so you can take a look at it. So likewise, I'm going to do just 2 more examples like that. Okay, so let me go down. So this is the image of the tangent plane we just found out. Okay, so this one, the bottom one, there are many lines passing through. I'm covering all that moment. That's the bottom one, the plane, tangent plane we just found out. So likewise, let's take a look at just a couple more examples. So I wrote down the equation of the tangent plane. So let's take a look at the following example too. So this is the equation. So we're gonna do step by step, and then here we have all 3 points. So we know z0, it's going to be f, x0, y0, right? And then at negative 1, 1, negative 2. So what are you guys gonna do? This is the equation, so negative 1 square, 3, negative 2 square, so we have a negative 2. So this is the f of x0, y0. And then partial derivative with respect to x, so d over dx, we have x second, 3y second, so that would be 2x. And then y is going to be constant, nothing there. And then x, we know negative 1, 1, negative 2. So 2x is going to be 2 times negative 1. We have a negative 2 of the partial, derivative with respect to x. So same thing, y. So d over dy, x second minus 3y second. So now in this time, x is a constant. So negative 3 times 2y, which is a negative 6y, at negative 1, 1, negative 2. So negative 6 times 1, negative 6. So we have that information. The z, the equation of tangent plane will be negative 2 plus negative 2, x minus x0, negative 1, plus y, we got negative 6, y minus 1. So now you're going to do all the distributive property. So this is negative 2x minus 2, negative 6y plus 6. So therefore, z equal to negative 2x minus 6y plus 2. That's the equation of the tangent plane at negative 1, 1, negative 2. So you feel like, oh, I can manage this type of question. I know you can do it. So now I'm going to give you a little bit complicated, the equation. So let's take a look at the example one more time. So here, the same tangent equation of the plane. So what happened? Ooh, we have sine and cosine, and they want to find out the tangent plane at pi over 3, pi over 4. So same strategy. We're going to find out f x0, y0. So sine 2 times pi over 3 times cosine 3 times pi over 4. So if you go to decimal, you can find out each sine, sine 2 pi over 3 times cosine 3 pi over 4. So that would be radical 3 over 2 times negative radical 2 over 2 which is negative 6 radical 6 over 4. So that's going to be the basic f of x0, y0. So now the next one, we are going to take the partial derivative. You can try, but let's take a look at it. d over dx sine 2x cosine 3y. So now we are taking the derivative with respect to x. So cosine 3y, it's going to be constant, but now you have to take the derivative of the sine 2x. That'll be, you have to remember d over dx sine nx. You're going to flip, actually my bad, not the flip, n times cosine nx. Do you remember this? So take a look at it. So what are you guys going to do? Let me just double check. D over dx sine nx. So let me see if yep, so this is the correct. So we are going to this one 2 times, what do you guys think? 2 times, we have a cosine nx, 2x, and then the cosine 3y, this is a constant, so we don't need to change anything. So that's the derivative, partial derivative with respect to x. I want to find out at pi over 3, pi over 4. So this is going to be 2 times cosine, 2 times pi over 3, cosine, we have a 3 pi over 4. So you can calculate them. That should be, go to decimal around negative radical 2 over 2. So this is a partial derivative, f of x, at pi over 3, comma pi over 4. So let's take a look at, keep on going. The y partial derivative. So d over dy sine 2x cosine 3y. So in this time, what? This is going to be your partial derivative. So sine 2x, that's going to be constant. So I'm going to keep sine 2x. And then cosine 3, this is going to be what? Cosine is going to be negative sine. So negative 3 nx. And then we have a sine, keep the same thing, 3y. So take a look at it. That's your derivative techniques. So that means we can rewrite it at pi over 3, comma, pi over 4, sine 2 pi over 3. And then negative, let me bring negative to the front. So negative 3 times sine 3 pi over 4. So you're going to calculate this. That should be around negative 3 with a radical 6 over 4. Almost. So we have all the information. So you're going to plugging it to the equation of the tangent plane. And then z equal to, what do you guys think? Negative 6 over, actually, radical 6. What was it? This one. Radical 6 over 4 plus radical 2 over 2, x minus x0, pi over 3 minus 3 radical 6, y minus pi over 4. We are going to, simplify this equation. So distributive property, radical 2 over 2x minus radical 2 pi over 6, 3 radical 6 over 4y, 3 radical 6 pi over 16. So if I just write down again, x is first, radical 2 over 2x minus 3 radical 6 over 4y, and then all the constants, radical 6 over 4, that's actually, I just put the wrong number. So this one, 2 pi, radical 2 pi over 6, 3 radical 6 pi over 60. So that's going to be the equation of the tangent plane. Okay, so far we've been exploring how to find out the equation of the tangent plane. I'm going to keep going on. So 4.4, they're going to show you many perspectives, on this concept. One is a tangent plane. The next one is a linear approximation. So let me take a look at that equation. Slowly, let's go. There's one more practice you can try to find out the, we talk about this. So you can practice this one, practice. So try this yourself. So same strategy you can try. All right, so what we're gonna do, I'm gonna talk about the linear approximation. So we already learned linear approximation concept in calculus 2. So what is a linear approximation? So if you have, if you remember a little bit of a background. So in calculus 2, oopsie. So if we remember, let's say I have a function. And then let's say you found out the tangent line right there. This is a tangent line. Something y equal to mx plus b. And then tangent line, you have a specific point, x equal to a. You have only one point that the line is touching, right? If you are touching 2 points, this is the equation. This is the just line equation. But tangent line, we are touching only 1 point. That's the definition of the tangent equation, correct? But let's say by using this tangent equation, we might be able to approximate what the outcome when, let's say, x equal to a plus 1. So there's a plus 1. Maybe by using this tangent line, I might be able to find out what the outcome. But as you see that, there's a little bit of gap. I'm going to just highlight that yellow. This is a little bit of gap. This is a little bit of arrow, okay? So, but still, we can approximately estimate what the outcome when x equal to a plus 1 by plugging in this one into the tangent equation. Maybe you can find out the outcome. So that was the concept of the linear approximation, even though you are not going to get the correct, precise answer. By using this tangent line, you can approximately estimate what the outcome when x equal to a plus 1, because tangent line is only touching 1 point. So we were able to find out the specific outcome. So let's say this is, I'm just giving you 16,4, but I want to know what is 6.3, what, right? But so you can still plugging into the linear, this tangent equation. So you can approximately estimate the outcome when x equal to 16.3. So we call this process linear approximation. By using this tangent line, you can estimate the outcome, although it's not precise. Still, there is a gap, right? These are all the arrow because your true value is here. Your tangent equation just approximately estimated. But still we can estimate it, right? So that's the concept of the linear approximation we learned in calculus 2, and that was the formula. So what we are doing here in calculus 3, the same situation is happening in 3-dimensional space. So let me go down slowly. Same concept here. You have, you have a tangent equation. So you have a tangent plane that they're touching one specific point, but by using this tangent plane, you might be able to estimate the next point information, although it's not, correct or precise. So this equation, same thing actually. Well, we got tangent, the equation of the tangent plane. So it's the same thing. You're gonna take the derivative, partial derivative x and y, and then we can find out the outcome by using this tangent plane. So let me write it. This is the equation of tangent plane, like the same thing, y equal to mx plus b tangent equation. You can estimate, we can estimate the outcome of small decimals, although they are not precise. So sounds a little bit weird, but I will show you one more time. What is a tangent line? Tangent line, it's a kind of like your prediction, right? This is your prediction. When you hit that moment, you can exactly find out the input and output. You can find out the clear output, 100%. You can predict your outcome, but your true information is here. This is your true function. You have points here. The tangent line, even though you're plugging in this input into the tangent equation, that doesn't mean that you have a correct outcome. Your correct outcome is still here. But by using tangent equation, you can approximately estimate the outcome. So that's what the linear approximation, that's what the role of the tangent equation or tangent plane in both the 2 and 3-dimensional space. Does it make sense to you? So a little bit of background. So I'm gonna just show you the image because this concept is not complicated, but one more time. Let's say I have a function, right? Or I'm gonna draw this way. So let's say this is your tangent line. They're touching exactly this moment. A, B, or I'm gonna just give you the number 3, 5, let's say that. When you have x equal to 3, you can estimate the outcome 100%, right? Because it's gonna be 5. But when you have the input, let's say 3.5, they're not really touching this tangent line because of this gap. This is the arrow. This is the arrow. This is the arrow. If you wanna find out 4.1, this is the arrow. You can still estimate what the outcome by plugging in y equal to mx plus b, but that doesn't mean that you are getting the true output, right? Because of this true outputs, these are the true outputs. So we call this is the residual, or we call this is the arrow. But again, like many industry, or you are talking about the stock, it's hard to predict the future value, 100%. There is always the arrow. Let's say tomorrow, let's say just an example, let's say I purchased a Tesla stock. So this is your mathematical modeling, okay? And then this model, tangent equation or tangent plane, they're estimating when you have 3, you're gonna find out the 5. Let's say that's their scenario. In 3 days you will get 5. Let's say $5. Maybe it's not, but the more time goes, the prediction said it's going down, 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 down. So this is your prediction. Okay, when you're passing through, let's say 4 days, the prediction is going to be about like $4 or $3. The price is getting dropped, but the true value is more and more dropped. This is a true story. And then the tangent line, you can think about it. This is your prediction. So tangent equation, it's the same like the prediction line. So there is an arrow. You see that? Nobody can estimate the arrow, perfectly. We are just estimating what's happening. It's like a probability question. So this is a tangent line. And then in 3-dimensional space, in more mathematical concept, you can also find out the arrow by looking at the gap between the true value and the linear approximation outcome. Okay, so think about it, this concept. It's a little bit interesting. So in calculus 2, this is the formula to, find out the linear approximation, which is the same as a tangent equation. And in 3-dimensional space, the equation of the tangent plane, we also call the linear approximation. Okay, so I will show you the example. So let's take a look at the concept and look at the example one more time. Let me go here. So let's take a look at it. We have a function. I want to estimate 2.1 to 2.9. Okay, there's a decimal. And then using 2.3, we want to know the estimation outcome or the function when the function is passing through 2.1 and 2.9. So let's step by step. First, find the equation of the tangent plane. Okay, so we know the formula. So that was the formula. So we can do f x0, y0. And then at, because we're going to use a simple, that's 2, 3 first. So let's take a look at what you're going to get. 41 minus 4 times 2 square minus 3 square. So if you calculate it, it's going to be 4. Radical 16 is a 4. Partial derivative. And then d over dx, right? And then this is a 41 minus 4x second minus y second. Radical is a half exponent, isn't it? So we are going to take the derivative. I'm going to bring 1 over 2. And then 1 over 2 minus 1. And then chain rule. And then it's with respect to x. So d over dx, the inside. So y is going to be the constant. So this is going to be negative 1 over 2, 0. And then the next one is 8x, negative 8x. Y is going to be the constant. So basically 2 and 4 cancel. Negative 4x over, because of the negative exponent, all the way down with the radical. So this is going to be partial derivative at, and then now I want to find out at 2, 3 first. So then if you plugging in 2 over 41, 4 times 2 square, 3 square, you should get negative 2. So this is the outcome, right? When you're passing through the 2, 3 in the plane, okay? Hold up there. We need to take the partial derivative with respect to y. So we're going to do the same work, fy, x0, y0, d over dy, 41 for x second, y second, half exponent. So 1 over 2, 41 for x second, y second, 1 over 2 minus 1 inside, d over dy, 41 for x second, y second. So that would be 1 over 2, 41 for x second, and negative 1 over 2. 41 gonna be 0, correct? And then for x second, that's gonna be 0. We have a negative 2y. So it would be 2 cancel, negative y over radical 41 for x second, y second. So now I want to find out at 2, 3, which is a negative 3 over 41, 4 times 2 square, 3 times the square. If you calculate it, that would be negative 3 over 4. So now let me complete the equation of the tangent plane. We've been practicing it. And then that z equal to, plugging in all the number we just got, 4 plus, and then minus 2, and then x minus x0, which is we use a 2, 3, so 2, plus negative 3 over 4, y minus 3. So if you simplify, and 3 over 4y plus 9 over 4. So this tangent, this equation of the tangent plane, it is also same as a linear approximation. So therefore, I'm going to just write it 2x. And then you're going to add in all the constant. That would be 41 over 4. So tangent equation is the same as a linear approximation equation. Now, we want to know the difference between when point 2, 3 and 2, 1 and 2, 9, right? So there's a 2 points. So let me plugging in linear approximation 2, 1, 2, 9. We have decimal, you can plugging in and simply calculate it. They are going to give you 3.875. So this is a linear approximation. This is the linear approximation of, or this is the tangent. This is the tangent, equal plane's outcome. But now, 1 second. I want to compare with the linear approximation with the just function. 2.1, 2.9. So this is the function. This is the function. And what? This is a linear approximation. In other words, this is a tangent equation. Sorry, this is the equation of the tangent plane, correct? So there's a two function going on. One is, this is a true function. So if you graph it, I don't know, let's say the function looks like this. And then the linear approximation, it's going to be based on the tangent line. So let's say this is a tangent line. So one is, this is Lx comma y. The pink is Fx comma y. You see the difference? So when you're plugging in 2.1 and 2.9 into the linear approximation, we got 3.875. And let me plugging in 2.1 and 2.2 into the function that they gave us, which is this one. So if you're plugging in, just let me minimize it. What happened? So here, 41 minus 4 times 2.1 to the, what was it? Second power, minus 2.9 to the second power. You should get 3.8665. You see the different number here? This is came from the linear approximation, which is a tangent line outcome. And then this is the true value from the function. So what that mean? This is what that mean. There is about 3.875 minus 3.8665. The difference is about 0.08 error between the linear approximation, which is a tangent plane, and the function. Okay, so that's what the conclusion. I just want to show you that process. So let's say we have here 2.1. When you hit the, this is when you hit the, let's say here, when you have a 2.1 and 2.9, when you're plugging in the linear approximation, you got the outcome 3.875. And then when you hit the function, you got the outcome 3.8665. The gap here, this is the error. And then that's about 8%. So what I'm saying is, tomorrow your Tesla stock might be, let's say 366 cents. I'm just, giving you the random number. And the approximation is saying a little bit higher. So nobody can guess on all the time, as a true value. So there is a gap, the tomorrow actually it's going to be fall down, but your prediction says it's going up. So that's the difference between tangent line and true value, or you can think about this is more related to the regression line. Okay, so think about it. This is, same concept, linear approximation is the same as a tangent plane equation. And then you can find out the error, how much, true, and the prediction has a gap. Okay, so that's the concept of the linear approximation. That's it. Okay, so I'm not going to spend too long, but you can think about it. So let me go to one more example. So let me go down. So let's take a look at this one. So same thing. They want you to find out the linearization. That means find out the tangent line. That means find out the tangent equation. Just we're going to change z, l, x, comma, y. Okay. So step by step, we're going to find out x0, y0 at 0, 2. So it is going to be 0 square, 2 square, sine. 2 times 0 is a 0, which is a 0. 4 plus a 0, you should get 4. And then partial derivative, at 0, 2. So let's take a derivative first. X second, y second, sine xy. So now y is going to be the constant. So that's going to be 0. X squared will be 2x. And then when you're taking the derivative of sine xy, this is the chain rule. So you are going to sine d over dx sine xy, and then xy has been inside and outside. So this is outside, this is inside. So you should get 2x, sine will be cosine xy, and xy, when you take the derivative of x, you should get y. So now at 0, 2, 0, cosine 0 times 2. So you should get 0. This is going to be 0. Cosine 0 is 1. 1 times 2 is 2. That's what you're going to get. One more, we need to find out the partial derivative with y. X 0, y 0 at 0, 2, d over dy, x second, y second, sine xy. So in this time, x is going to be the constant, so you should get 2y. Same thing outside, this one dy, sine xy, d over dy, xy. So you can see the structure inside, outside. So 2y plus sine will be cosine xy. And then this is going to be x. So you should get plugging in 0, 2 cosine 0 times 0. So these are all 0. We should get 4. So now what you're going to get? The linear approximation. So we have this formula is the same as L. Right? So now we have all those 3, which is right there. 4 plus 2, x minus 0, 4, y minus 2. So therefore, the linear approximation at 0, 2, we're just plugging in all the number already. Minus 0, 4y 8. So L 0, 2, 2x plus 4y, and minus 4. So that's the linear approximation equation. Another is equation of the tangent plane. So now you can, if they're giving you any other number, you can find out the arrow between this and the regular function. So think about that relationship. Okay, but most of the question going to ask you, just find out the linear equation, which means tangent plane equation. Okay, so that's all about it. So we talk about so far 2 concepts: how to define the equation of the tangent plane, and then what the meaning of the linear approximation. Okay, think about it. The last concept, let me go down. Okay, here we go. Differentiability. So I'm going to read it slowly. So when working with the function y equal to f of x, one variable, the function is said to be differentiable. So what does it mean? If you have a function and then you can take the derivative, that means the given function, there's no hole, there's no break, it's a continuously smooth, right? So that's a required to take the derivative. So same thing in 3-dimensional space, when you're dealing with the 2 variable, in the surface, right? When you're talking about the plane, let's say there's a 2 point, x is 0, y is 0. If you want to find out this equation, there should be no hole, there's no break. It should be smooth point. It should be smooth plane of the tangent line. So this is the thing. We already know the tangent plane equation, correct? This is going to be always differentiated when the function, okay, when the given function is smooth and there's no break and don't hold, then you can take the partial derivative. So just it's the same meaning. We already been practicing how to take the derivative to find out the equation of the tangent plane. But here, tangent plane exists at that point. The partial derivative must therefore exist at that point, which means that the function of two variable. So to satisfy the sentence, there is no hole or break in the function of two variables. So same condition, like one variable we talk about in calculus 1 and 2. So I'm going to keep going. Actually, I want to talk about the arrow, right? We just talk about the arrow. There is an arrow between, if you remember, this is the function. Let's say this is the tangent plane. So let's say you have a tangent plane and this is the function. There is an arrow, right? These are all the arrow. It's hard to imagine, but we can imagine abstractly. There's an arrow going on, right? So how to find out the arrow? One way is you're going to look at the relationship between linear approximation and the regular function, and you can see the difference. Another one is you can just use this information. Let's take a look at it. This is a tangent equation. And then we know that there is an arrow in the outcomes between equation of tangent, or I'm going to say linear approximation, between linear approximation and the given function. We just talked about it, right? So if you go up, actually in this question, this is the linear approximation outcome. This is a function outcome. We found out the gap right there. So what does it mean, the gap? In other words, here, the tangent plane, the equation of the tangent plane, right, has always the arrow, right? So to find out the arrow, we are going to find out the limit. Okay, whether it is a 0, that's good, there's no gap. If there's no, if you found out some number by taking the limit, then there's a limit, there's an arrow existed. So this is the arrow function. So this is arrow. So that's all the talking about the same thing, right? So we're gonna take a look at the example. The concept, it's a little bit like a lot of boarding, but if you look at more visualized concept, we found out the outcomes between linear approximation and function, there is a gap because your tangent equation does not predict the outcome always perfectly. There's always a true story and there's a prediction story. There are two stories are going on. Some people believe that tomorrow the stock is going to be going down, or some people believe that it's going up. There's always an arrow between two mathematical modeling. So therefore, there's an arrow existed. And then how to check the arrow? If it is a 0, that's a good. You don't have an arrow. You can, no matter which model you're choosing, you're going to be perfect. You're going to be always right. But it's not, happening all the time like that. So we are going to check the limit. Okay, so that's something, the way you are going to find out the better modeling. Okay, so let me go to the next example. So here, just take a look at that example. So here, let's do this one. I have a given equation. I want to find out if this one has an arrow or not. So f of xy equal to, this is the tangent. You can write down the equation of the tangent plane. Actually, I'm going to write, we already have that. I think I have it here, right? So here, so we have f x y. This is a equation of the tangent plane. And then we might be able to we might have a arrow. I don't know what that is. Okay. If it is a 0, okay, there's no arrow. If there's no 0, there's an arrow, right? So let's find out the equation of the tangent line one more time. So f x0, y0 at 2, at 2 comma negative 3. So 2 times 2 square minus 4 times negative 3. 4, 8 minus plus 12, you should get 20. And then partial derivative at 2 comma negative 3. So d over dx, 2x second minus 4y, 4x, that's going to be constant. So 4 times 2, you will get 8. Fy at 2 comma negative 3, d over dy this time, 2x second, 4y, x is a constant. So you should get just negative 4. That's what this is a constant. So we don't need to, plug in anything. That's what it is. So therefore, this one, we got the equation of the tangent plane. 20 plus 8, x minus 2, and then negative 4, x plus 3. Because a negative 3 will be positive. So in other words, 20, I'm going to use all the distributive property, 8x minus 16, 4x minus 12. So basically, 8x minus 4x minus 8, right? That's going to be fxy. But we know that there's going to be an arrow. We know there's an arrow because we should find out the difference between the linear approximation and then function outcome has an arrow. If we are going to check if the arrow is a 0 or not, right? Because there exists an arrow between linear approximation Lx, y outcomes and the function outcomes, right? We know that there's an error going on. If it is a 0, that's a perfect. You can choose either whatever you want. You can use either linear approximation equation or the function equation. So we are going to check how to check the E. There's a formula, go up, right there. So E, we are going to find out the arrow, whether it is a 0 or not. So limit x comma y, go to x0, y0, E x comma y over radical x minus x0 square plus y minus y0 square. So let's do the work. So we found out, okay, this equation, I'm gonna bring this, so this one, we actually stop here. So I'm gonna copy this, copy, and here. So we know what happened. The f of xy, this is the given function. I'm gonna plugging in this one. So this is the same as 2x second minus 4y equal to 8x minus 4x minus 8 plus ex comma y. Let's solve for e. I'm going to bring all the way. I'm going to bring this one to the other side. So 2x second minus going to be plus 4x minus 4y plus 8. This is going to be what happened. Let me just double check. Did I write down the same thing? So let me just look at that. We have a 8x minus 16. Oh, I have a little bit of an arrow. You see that? This one should be y. Why did I put them? So this one should be y, because this is x minus x0, y minus y0. So this one should be y. So 4y, my bad. So 8x minus 4 y, 20 minus 16, negative 12. Yeah, negative 8. Sorry about that. So I have to recalculate it. This one is a y. So we have, this one is y. So you have, this is y. So what happened? They're going to be canceled. So this is going to be arrow E, 2x second plus 8. That's going to be your arrow. So we have this formula. You have this formula. So I'm going to bring here a little bit of work. So I'm going to copy this, paste. So we found out this is equal to, we have E 2x second plus 8 over. And then we are going to take the limit. X comma y go to where? 2 comma 3. If you go up, 2 comma negative 3. 2 comma negative 3. So x minus 2 square, y minus minus 3 plus the 3 square. So you're going to take the limit of that ugly fraction. So just a little bit of space. Okay, so I'm going to simplify limit x comma y. They're going to 2 comma negative 3. And then I can find out the factor. So let me just double check. 2x second power negative, sorry, why I have a mistake here. So here, sorry about that. So when you actually recalculate this one, you see that, where's my mistake? 2x second minus 4y, negative 8x plus 4y plus 8 equal to ex comma y. Only 4y plus, they cancel, so we have a 2x second, negative x plus 8x plus 8. So this one, I have a little bit of a negative 8x plus 8. That was ex comma y. I'm going to factor out to x second minus 4x plus 4 over, we have a radical, x minus 2 square, y plus the 3 square. So what are you guys going to do? I'm going to simplify limit x comma y, hang in there, 2 comma negative 3. X, this is going to be x minus 2 to the square. And then I have x minus 2 square, y plus 3 square. So I just want to know whether this is a 0 or not. Right? This is your arrow, correct? So when you look at this, I'm going to just copy this. Copy, paste. This information, it's hard to evaluate it because if you're plugging in, we just want to know whether it is a 0 or a negative number. We want to know this is going to be negative outcome or positive outcome or 0 outcome. So what I'm going to do, I'm going to compare this one with the similar. So what I'm going to, let me copy, same thing. If you, here, let me just plus y plus 3 to the second power. So what I'm going to do, we know that this is the regular, this is the regular, but I'm another fraction, just adding the similar one, y plus 3 to the second power. When you compare the size, always the right side is going to be larger because think about it. Let's say this is 2 over 3. Now you 2 over 5. Let's say this is going to be 3 over 5. So by adding the something in the numerator, the right side is going to be larger because this is hard to solve it. And then now I'm going to solve this one. What happened? So this one, 2x minus 2 to the second plus y plus 3 to the second, correct? And the bottom is going to be x minus 2 to the second y plus 3 to the second, and I have a half exponent because of the radical. This one, because you know the characteristic of the exponent, this is the same as, so there's entire invisible one, 2x minus 2 to the second, y plus 3 to the second, and then what happened? According to the exponent rule, 1 minus 1 over 2. Do you remember? So note, you know, you have AB over AB to the 2. This is AB, 1 minus 2. So we are applying this one. So therefore, you can check. We are going to take the limit, right? So it is going to be, if I solve it, this is the positive. No matter what you're plugging in, because of the second power, it is going to be the positive, isn't it? And then this is going to be positive. So limit 2x minus 2 to the second plus y plus 3 to the second. We have this. What I, for any x and y, the outcome of, let's say this is the star is always positive. So since this is a positive, what do you guys think? This is also going to be the positive because of the comparison theorem. Thus, this is your true E, the arrow. Therefore, the arrow x comma y is also greater than or equal to 0. So in this function, a little bit of sentence. So a little bit of, you know, we have a lot of story. I just want to make sure this is a differentiable. So we found out the tangent equation of the tangent plane, and then there is an arrow. We believe that we check that the arrow by using that formula. We check. We found out the arrow existed. Arrow exists, but we are not sure. It could be also 0. So the conclusion is the function we have 2x second minus 4y, that is a differentiable at 2 comma negative 3 because the arrow can be 0 or positive. That's it. No more. One more time. The last part might be confusing, but let me show you one more time. Everybody can find out the equation of the tangent plane, but then we know that there's a possibility the arrow exists. So we are checking if the arrow can be 0 or not. So by looking at the limit, the definition of the arrow, we found out the outcome of the arrow by using the comparison theorem. So the comparison theorem says that, you know, whatever you plugging in number into x and y, the outcome is going to be positive because of this positive exponent. So what does it mean? There's a possibility because of the equal. There's a possibility arrow can be 0. So therefore, this function is a differentiable because the arrow can be 0. So that's the conclusion. Go up here. We are checking whether this function is a differentiable or not, which means at that moment, there's no hole, there's no break if it is a differentiable. So we just check that there's a possibility the arrow can be equal to 0. Therefore, at that moment, 2 comma negative 3, this function has a no hole, has a no break. It's a smooth, which means it's a differentiable. So that's how you're checking differentiability by looking at the arrow equal to 0. Okay, so this is the last concept for 4.4. And then all you need to do, check the arrow part, whether there's a possibility it could be 0, okay? Then, you know, your function at that moment can be differentiable, which means there's no hole, there's no break. So today we talk a lot, right? So just go back to the objective. We talk about how to find out the equation of the tangent line. We also think about the concept of approximation, the linear approximation of two variables. And then from there, we talk about the concept of the arrow between linear approximation and the regular function, right? So there's a formula to find out the arrow all the way down. We just talked about in the last question. So think about, these are all related concept for point 4. And then we finished so far. And I hope this video helps you to understand better. You know, calculus 3, I don't want to say this is a challenging topic, just you're expanding your knowledge from 2 to 3 dimensional space. And then just more, integral, derivative techniques, but you already learned that from calculus 1 and 2. Okay, so 4.4 tangent plane and linear approximation, it should be okay. So you can finish the quiz, and there are more embedded video you can watch. Also, if you have questions, you know what to do. Go to discussion board and engaging with other people, or email me if you need more extra help. Okay. Thank you, everyone. I will see you guys in the next video. Have a great day. Bye-bye.